Hello everyone, welcome back to the lecture series on analog electronics. Lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. In the last lecture, we saw the modeling of transistor and how we can use that model for analyzing the small signal response of an amplifier, right? So today we will go for more circuits and we will analyze them all. So let's go. Our first circuit is called common emitter configuration, that 2 voltage divider bias, but without the bypass capacitor. Let's write it. Common emitter configuration now we know the circuit. This is the circuit. Here we have VCC, R1, R2, this is RC, this is RE, and here we have CI and CO. Now this is connected to our source, so there is the source resistance RS, and here we have our source, that is the signal. This is Vs, this is Rs. Now we can analyze this circuit using the RE model of transistor. Okay, let's get into it. But we know that before we get into applying the model, we need to prepare this circuit. So let's prepare this. So this can also be drawn as, this is our Vs. We are doing the AC analysis, so DC supply has to be connected to the ground. This is all the way connected to the base. Here we have a resistor, which is RE. Here we have R2, which is also connected to the ground, one end of it. Here we have R1, one end of it is now connected to the ground because we have removed the DC supply. Then there is RC, again connected to the ground. We are assuming that load is open. So here we have our output. So Ci and Co offers zero reactance to this particular frequency, and they can be considered as short circuits. So our circuit has become like this. Now we can draw the equivalent circuit. So it is drawn here. We have a ground. There is Vs here connected to the ground. Rs. Here we have Rb. We have already seen what Rb is. Rb is equal to R1 parallel R2. Now here we have the transistor, which can be replaced by its equivalent circuit. So this is base. Now at the emitter we have Re. Now this is emitter. Between emitter and ground there is another resistance Re, because this is unbypassed. So Re is still there. Here we have Ib. Now here we have alpha IE, but since our input is Ib, this current can be written as beta IB. Beta IB and alpha IE are the same. So I am replacing this by beta IB. Here there is the collector, and between collector and ground there is our RC. And here we have our output. So this is the equivalent circuit in RE model. Okay, now let's start solving for the important parameters that we know, that is input impedance, output impedance, voltage gain and current gain. So when you look from here, we have Rin. When you look from here, we have Rin dash. When you look from here, we have Z out or R out, because I have already told you that these transistors will have resistances at the input, because all the capacitance are removed in the small signal low frequency analysis. So all these impedances are now just resistance, and that's it. So this is our equivalent circuit. I am redrawing it again for better understanding. Here there is Vs connected to the ground, Rs, Rb, then here we have Re and Re, a current source which is beta Ib, and here the resistance Rc. Here we have the output. This is Rs, this is Rb, this is Re, capital Re, this is Rc. Now we know that Ib flows here, IE flows here, and this is beta Ib. Here it is open, there is no load resistance, and I out flows here, because in two port notation we know that the current enters the port. So if I out flows here, the current enters the port. Alright, now this is Rin and this is Rin dash. Here we have Vi. Now Rin dash is nothing but the input impedance Zi. Here we have Ii. Alright, also when you look here from the output side, you can see Z out. Now we can find out the parameters. So the first parameter is input impedance, which is Zi, which is given by Vi divided by Ii. In order to find out Zi, we will first find out Rin. Rin is given by the voltage across these 2 points, that is between base and ground, and which is also equal to Vi. So Vi divided by the current here, which is Ib. Now Vi can be written as Ia into Re plus Re. Now that divided by Ib will give Rin. Now IE can be written as beta plus 1 into Ib. The rest is small re plus capital Re divided by Ib. So Ib cancels, and Rin will be equal to beta plus 1 into Re plus Re. Now we can make an approximation here. That approximation is, since beta is very much greater than 1, beta plus 1 will be equal to beta. So that will give Rin equal to, is approximately equal to beta into Re plus Re. Now we also know that the value of Re is very much greater than the value of Re. That means Rin is now approximately equal to beta times Re. So we can use these approximations to solve our problems. It will not change the values much. So Rin is equal to beta times Re, and what will be Zi or Rin dash? It will be equal to the parallel combination of these two resistances, right? So Zi will be equal to RB, which is R1 parallel R2 parallel Rin. So this is Zi. Now we can find out the output impedance. Z out. So Z out is given by V out divided by I out when input is equal to 0. So if we make the input 0, IB will be equal to 0. If IB is equal to 0, this current controlled current source will become an open circuit. So that means when you look from here, the only resistance you can see is RC. So Z out will be equal to RC. This is the value of output impedance. Now we can find out the voltage gain, AV. We know that AV is given by V out divided by V in. Now look at the output. IO flows here through RC and the direction of V out is like this. So what will be V out in terms of these two? V out will be minus IO into RC. Now V in will be equal to, or Vi will be equal to the voltage across this, and that we have already found out, which is IA into RE plus RE. So Vi is equal to IA into RE plus RE so AV is equal to minus I out into RC divided by IE into RE plus RE. Now I out is nothing but this one, because if you look at I out, this is flowing as beta IB because this is open circuit. So this can be written as minus beta IB into C divided by IE can be written as beta plus 1 into IB, and the rest is RE plus RE. Now this will give us IB and IB cancels, so minus beta RC divided by beta plus 1 into RE plus RE, and we approximate beta plus 1 to beta. This will be equal to minus RC divided by RE plus RE, because beta and beta cancels. So AV can be derived as minus RC divided by RE plus RE, small RE plus capital RE. Now the last parameter is current gain. Current gain AI is given by I out divided by I in. Now if you look at the input circuit, this is I in, this is flowing here, and some part of it is going into the transistor as IB. So we can find out a relation between II and IB. So if you look here, IB flows here, there are two parallel resistance, and IB is the current through this resistance. So that means we can apply current division rule here, and by current division rule we will get IB as II into RB divided by the resistance here is after RB is nothing but Rin. So RB plus Rin. Now we know the approximation for Rin, which is beta RE. So this can be written as II into RB divided by RB plus beta RE. Now from this we will get a relation between IB and II, and that will be equal to RB divided by RB plus beta RE. Now the value of AI, which is I out divided by II, can be written as I out divided by IB into IB divided by II. We have already found the relationship between IB and II. If we look at I out and IB, we can see that I out is nothing but beta IB, right? So I out divided by IB will be nothing but beta. So this is equal to beta into IB by I is RB divided by RB plus beta RE. So this is AI. There is one more thing, that is this small RE is very much less than RE. So AV can again be approximated, and that gives us AV is equal to minus RC divided by RE. So this can be used to find AV. Now let's do a problem. So here we have a question. This is an emitter bypassed common emitter amplifier with voltage divider bias. Let beta and all the capacitor values are very large. Take VB equal to 0.7 volt and RE is equal to 25 millivolt divided by IE. This is obtained by the relation RE is equal to VT divided by IE, where VT is the thermal voltage and the thermal voltage in room temperature is 25 millivolt. So for finding out RE, you can use this relationship anywhere, that is RE is equal to 25 millivolt divided by IE. IE is the DC value of emitter current. Now our first thing is find the value of DC current IC. Then second question is mid-band voltage gain. So this is our clue. So we are told to find the mid-band voltage gain. That means we need to find the small frequency voltage gain of this circuit, because up to mid-band we assume that the amplifier is in its low frequency range. So low frequencies and mid-band frequencies corresponds to the small signal low frequency analysis. So first one is find the value of DC current IC. For that we can convert this into its corresponding DC equivalent circuit. Let me write it here, DC equivalent. For that capacitors are open circuited and source is removed. Now these resistances 20k and 10k, they are combined into their Thevenin's equivalent. So I am going to draw that circuit because we have already done this type of problems. Now V Thevenin can be found out from the voltage divider, which will give us 9 into the voltage across this, that is the V Thevenin, that is the voltage across 10 kilo ohm resistor. So 9 into 10 divided by, that is 10k divided by 20k plus 10k, that is 9 into 10k divided by 30k, kk cancels, 10 and 30. So what is left is 3 volt. So V Thevenin is equal to 3 volt and RB is nothing but the parallel combination of R1 and R2, and this will be given by, you know, the parallel combination of 20k and 10k, 20k into 10k divided by 30k, that will give us 6.66 kilo ohms. Now we know how to find out the value of current IB. IB is given by V Thevenin minus VBE divided by the resistance RB plus beta plus 1 into RE. Now in the question it is given that beta is very large. So even if we find out IB using this, it will only be a few microamperes. So IB can be approximated to 0 microampere. Now we can find out the value of IE from here. This is the value of IE. Now if IB is equal to 0, this resistance RB will not have any drop in it, right? If IB is 0, IB into RB will also be 0. So the drop in RB is 0. That means now RB will be like a short circuit. So what is left in this circuit, in the input circuit? We only have VThevenin, which is 3 volt, and 0.7 volt drop between base and emitter, and 2.3 kilo ohms as the resistance between emitter and ground. So from this we can find out the value of IE, and IE will be equal to 3, which is VThevenin, minus 0.7, which is VBE, divided by 2.3K, which is RE. So these are all approximations. This will give us an okay result. Okay, this is not accurate, but this is enough. So this is 2.3 volt divided by 2.3K, and that will give us 1 milliampere. So the value of IA is 1 milliampere. Since IB is 0, the value of IC will also be 1 milliampere. So we have solved the first question. We have resorted to this because we don't know beta. Okay. Now we can find out RE. So RE will be given by 25 millivolt divided by IA, which is 1 milliampere. That means RE is equal to 25 ohms. Now we can draw the equivalent circuit of this for mid-band voltage gain. That is, we are going to do the AC analysis. So for DC current we did DC analysis in the previous slides. For AC analysis, first we have to remove the AC sources. Capacitors are assumed to be short circuits, and then we will draw the circuit. So the circuit will look like this. Since we have found out RE, we can use the RE model. This is connected to the base. From base we have the RE. Since there is a bypass capacitor, this resistance is now shorted out. So there is only RE here. Now here we have alpha IE, because we don't know beta. This is alpha IE, and this is the collector, and across the collector we have this 3K. This is 25 ohms. This is 3 kilo ohms, and between this point and ground we have our V out. Now we don't know Vs and Rs, so the voltage gain that we can find out is the voltage gain of the amplifier, not that of the system. So let me redraw. This is 10K. Here we have V in. This is IB. Now what we need to find out is AV equal to V out divided by Vi. Sorry, there is one more resistance here, that is there is RC as well as RL. So there is one more resistance here, which is, since they are both the same, we call this RC. This is 3K, this is RL, this is also 3K. Now this is our equivalent circuit. Now we can redraw this again. That is, since we don't need this, I am removing this from the circuit. So this becomes like this. This 10K and 20K will make 6.67K, which is the parallel combination of 10K and 20K. Now here we have the base, and here the emitter resistor RE, which is 25 ohms. Here alpha E is coming. Here we have a resistance, which is the combination of 3K and 3K. Since they are parallel, this is 1.5K. Now across this we have our output. Now we know that beta is a very large value. So since beta is very much greater than 1, what will be the value of alpha? Alpha is beta by beta plus 1. Since beta is very large, this becomes equal to 1. So we can write this alpha IE as just IE. Here we have IB, and here we have IE. Okay. At the output side, the only current that is flowing is this one, alpha IE. So through this resistance, in this direction, the current will be minus IE. So V out can be written as minus IE, since we have approximated alpha IE to IE, into the resistance here is 1.5K. 1.5K. Now Vin is equal to, from this figure you can see that this is nothing but Vi. So Vi is nothing but IE into RE. So Vi is equal to IE into RE. So AV is given by V out by Vi, which is equal to minus IE into 1.5K divided by IE into RE. RE is 25 ohm. Now that will be equal to minus 60. So this is the voltage gain of this amplifier. Thus AV is equal to minus 60. Okay. So here we have analyzed two circuits using two different models and did a problem. Now we will analyze one more circuit. So far we have only been discussing common emitter configurations. So in the next discussion we will be analyzing the common collector configuration. So next one is common collector configuration. And the circuit you are going to see is called emitter follower circuit. So the circuit is like this. There is our transistor. Now the collector is directly connected to VCC. There is no resistance in between. And here we have our biasing. Here we have emitter resistor. Here the coupling capacitors, source, and source resistance, Vs, Rs, this is Cc, this is R1 and R2, and this is Re. Now the difference is, in common emitter configuration, the output was taken from the collector, right? So in common collector configuration or the emitter follower circuit, the output is taken at the emitter. So here we have a coupling capacitor Cc, and our load resistance RL. Now across the load resistance we have our output voltage. This is RL. Okay, now we can do the AC analysis. So before that we'll prepare the transistor. So it can be redrawn as, there is a transistor. Now DC sources are removed and those points are connected to the ground. So collector is directly connected to the ground. One end of resistance R1 is connected to ground. One end of resistor R2 is also connected to ground. It was already connected to ground. There is RE here. All the capacitors are assumed to be short circuits. So here we have RL. And across RL we have Vout. This capacitor is also short circuited. Here we have RS and here we have Vs, our supply. So this is the circuit we have prepared for AC analysis. Now what is the next step? In the next step we will transform this transistor to its equivalent model. So here we are going to use the current controlled current source type of pi model. Okay, so I can redraw this figure. Here we have Vs, here we have Rs, then a parallel resistance combination of R1 and R2. This R1 and R2 are parallel, so they can be combined to form RB, and RB is R1 parallel R2. And here our base is connected, where we have R pi, the current controlled current source. Instead of GMVBE, we are going to use beta IB. My aim is to make you familiar with all these models. So that's it. And this is the collector. So collector is connected to the ground. Here we have the resistance R out, small r, small r. At the emitter we have RE, end of RE is grounded, this is also grounded, this is also grounded. This is RE, this is R pi, and what is left is this RL, and RL is connected here. And across RL we have V out. So this is our equivalent circuit. Now we can start the analysis. Before that, you can write this: RB is equal to R1 parallel R2. Now we can identify the input and output parameters, that is, the resistance seen when we look from here is Rn, and the resistance seen when we look from here is Rn dash, and Rn dash and Zi are the same. When we look from the output side, the resistance we see is Ro, and this is same as Zo, and the resistance seen from here is Ro dash. Okay, now we know that current IE flow here, current IB flows here, and beta IB flows here, right? So what will be V out? V out will be equal to IE into the parallel combination of RE and RL. So this is V out is equal to IE into RE parallel RL, and we know that IE is beta plus 1 IB, So V out is beta plus 1 into IB into RE parallel RL. Now if we look here, the voltage across this is VBE, that is between base and emitter, the voltage is VBE, and between base and ground, the voltage is VI. This is the input voltage to the amplifier. So VI can be written as VBE plus V out. Because between emitter and ground we have V out, and between base and emitter we have VBE. So VI can be written as VBE plus V out. Now from this figure we can find out VBE, and VBA is equal to IB into R pi. So VI can be written as IB into R pi, and we have already found out V out, which is beta plus 1 into IB into RE parallel RL. So beta plus 1 into IB into RE parallel RL. Now this is VI. So what will be V out divided by VI? Nothing but AV, the voltage gain, and that will be equal to this divided by this. So that will give you beta plus 1 IB into RE parallel RL divided by R pi plus beta plus 1 IB into R pi plus beta plus 1 IB into RE parallel RL. IB cancels from numerator and denominator. So what we get is beta plus 1 into RE parallel RL divided by R pi plus beta plus 1 into RE parallel RL. So this is the value of AV in emitter follower circuit. We can make an approximation here, that is, if 1 plus beta into RE parallel RL is very much greater than R pi, that is normally the case, AV is equal to 1. So this circuit has an output which is same as the input voltage. Yeah, AV is equal to 1. Now the next thing is the current gain. AI. AI is equal to I out divided by II. Now I out can be approximated to 1 plus beta into IB, and II can be approximated to IB. So we'll get an approximate result for AI that is sufficient. That gives AI is equal to 1 plus beta. So this is the current gain in emitter follower circuit. Now we can find out the value of input impedance. In order to find input impedance, we will first find Rn. Rn is the resistance when we look to the amplifier from here. So from here the voltage is the voltage across base and ground, which is the same as Vi, and the current going into the base is Ib. So Rn can be written as Vi divided by Ib. Now we already know what Vi is, which is Ib into R pi plus beta plus 1 into Ib into Re parallel RL. So this is Ib into R pi plus beta plus 1 Ib into Re parallel RL, and divided by Ib, you will get Rn, which is equal to R pi plus beta plus 1 into RE parallel RL. Now we will make two approximations here. One is beta is very much greater than 1, and the second one is beta plus 1 into RE parallel RL is very much greater than R pi. This will give us an approximation for Rn, which is equal to beta into RE parallel RL. So this is Rn. Now if we look at the figure, Zi is Rn parallel this Rb. So Zi, which is the input impedance, is Rb parallel Rn. Now this can be approximated as Rb parallel beta into Re parallel Rn. This is Zi. Now the last parameter is output impedance. Which is denoted by ZO. ZO cannot be that easily found out as before. Here you need to remember how we used to find. Here you need to remember how we find out the Thevenin resistance when there is controlled sources. When there is controlled sources. Okay. So this is our output. We need to find out the Thevenin equivalent resistance across this point, that is across the output, which is between emitter and ground. So the first thing we will do is we will remove the resistance, we will remove the supply if any is present. So this voltage source will be short circuited. Now there is a parallel resistance combination of Rs and Rb here, then R pi is here. Now there is no resistance here, and we have beta IB here. So we can arrive at a circuit that looks like this. I am also considering that since Ro is a very large value, Ro can be approximated to be equal to infinity. So this will be an open circuit. Okay, so we can arrive at a new circuit that looks like this. There is one resistance here, then our R pi here, then here we have removed the resistance, here there is ground, and here we have beta IB. Here also we have ground. This is also grounded. I am calling this RB dash, and RB dash is nothing but RB parallel RS. The combination of RB and RS. Since we have removed this source, RS is now grounded. So this is the parallel combination of RB and RS. So this is our new circuit. So in circuits that contain control sources, we can find out the value of R Thevenin. This across this we have to find R Thevenin by applying a voltage source here, a voltage source of unit magnitude, and then we can find the current that is flowing here. If we divide the voltage by this current, we will get the value of R Thevenin. Right? You might be remembering this. So we need to find this current I. We can apply KVL in this loop. Now here the current that is flowing is IB. So the equation of this loop is IB into R pi plus IB into RB dash is equal to minus 1 volt. From this, IB is equal to minus 1 divided by R pi plus RB dash. So this is the value of IB. Now at this junction we can apply KCL. IB is flowing here, beta IB is flowing here, and I is flowing in this direction. That means I plus IB plus beta IB is equal to 0. That means I is equal to minus of 1 plus beta into IB. Now we know what is IB. We can substitute it here. We will get minus of 1 plus beta into minus 1 divided by R pi plus RB dash. Minus minus cancels. So I is given by 1 plus beta divided by R pi plus RB dash. So the resistance here will be V divided by I. You can write RO is equal to V divided by I. V is 1, so it is 1 by I, which is given by R pi plus RB dash divided by 1 plus beta. So this output resistance is nothing but the output impedance. So output impedance is given by RB dash plus R pi divided by 1 plus beta. Now if Rs is equal to 0, that is if there is no source resistance, then RB dash will become equal to 0 because source resistance is parallel to RB. So RB dash is equal to 0. That means Z out is equal to R pi divided by 1 plus beta, and this is nothing but RE. So we have seen some more analysis of different configurations, different amplifiers. So now you will be at a position to do more analysis by yourself. Don't worry, we'll do some more problems. Okay, so far we have done only one problem with analysis. So I'm stopping here. We'll see in the upcoming lectures with more analysis and more problems. Until then,